So we just got started in the last class talking about photons, and just to kind of so the video would be uploaded probably within the 1 or 2 days for the last class. For those who couldn't make it yesterday to the extra class that was held in the late afternoon, early evening. But what we kind of did yesterday was talk quite a bit about phonons, and I stressed that conceptually there is really not much of a difference between phonons and photons, but obviously we know that there is a difference, and we are going to look at that specifically today. But the idea is the experimental if I were to take a piece of semiconductor and I shine on it a light or photons of energy h bar omega, and I start sweeping at from very, very small energies to few millielectron volt or very, very long wavelength deep in the infrared, and then I start so there's microwaves almost, and then you go to radio waves, and you know, kind of reach visible is around a couple of electron volts. 2 eV is when you will reach visible wavelengths in the red and blue and all that. So typically band gaps of semiconductors are around that value, and we talked a little bit about how all these little details can be picked up when light interacts with the semiconductor. You can see phonons, you can see free carrier absorption, you can see donor states, acceptor states, because of transitions between, here to there to there, and on all possibilities. You can kind of pick all of them up. But by far the strongest transition, we said, was going to be when electrons absorb a photon and get scattered or raised in energy to the conduction band. And that is what we're calling as interband absorption, and that process, or the value quantitatively is written as an absorption coefficient. And we said that we are going to calculate this absorption coefficient now, and show that absorption coefficient as a function of the photon energy. So if I were to kind of even say qualitatively how it should look, I should be able to say that for photon energies below the band gap, there's not much absorption going on. If I'm looking at the interband process, and then when I hit the band gap, the photon energy reaches the band gap, it starts absorbing very strong. So, and what we'll see now is this absorption coefficient. In the end of towards the end of the class today, what we'll see is it's given by a certain coefficient. And that sometimes this value I'm writing now would be absorbed in that coefficient and all that. But let me. So there is there's a matrix element between that couples the conduction band states with the valence band states. It appears as a square, and all matrix elements appear as a square because of the Fermi-Golden rule. It squares the matrix element. And then finally, what we'll have here is a joint density of states. In general, some books would write it as rho and density of states, which combines all the physics of the semiconductor, which is kind of buried inside the band gap, and some of it is buried outside here, and that of the photon. And the photon has an energy h bar omega. So it's a joint density of states that couples the light or the photon with the matter, which is the electron in the solid. So that's a joint density. So, and what I'm trying to say is this is what we may call as an equilibrium absorption coefficient. But to be more accurate, we must have the valence band states occupied, and we will see that we'll get a difference between the valence band occupation function minus the conduction band occupation function. Yeah, there's a question.
Yeah, could you say that again in regards to what rho of R is?
We will derive it in great detail now, but in general, this rho of R is, for example, in 3 dimensions. We will see it is, it looks something like this. Okay, so let's say there's a spin and a valley degeneracies and all that, and instead of a electron effective mass or a hole effective mass, you will have a joint effective mass. 1 over conduction band effective mass plus 1 over valence band effective mass is what's going to appear. It's called a reduced effective mass times square root of h bar omega minus Eg. That's what this whole quantity is going to look like. And if you look at it, this is very similar to the normal density of states that you have talked about before, except the normal density of states is defined separately for conduction band and separately for valence band. For the conduction band, that's m star C, or the conduction band effective mass. For valence band, it's m star V. For conduction band, this thing starts when the electron energy when the energy is at the band edge, conduction band edge, and then it, so for a conduction band, that would look like m star C, and this quantity will look like E minus EC, right? For valence band, that would look like m star V, and that would look like EV minus E, so it's flipped around. Here, so essentially you have the difference of the two appear here, band gap. Now this is new, this is the photon energy. Right? So because the experiment we're trying to explain is when I have photons incident on a semiconductor, and when does it start absorbing? Right? So, and here, because it's a transition between electrons in a valence band to electron states in the conduction band, the m star V from here appears and m star C of here appears. Both of them get mixed up, and then we'll get a reduced effective mass now. So that's we are going to end up here, after going through the whole process. It's how looking at it microscopically in detail. Now this is a very general relation. Whatever I wrote here, it appears, specifically if I have a 3-dimensional bulk semiconductor, this is the result I will get. But if I have a quantum well, then instead of the 3D looking picture, you will get a step, just like the density of states of quantum well looks like steps. That's how it's going to look for quantum wells. Quantum dots, it will look more discrete functions, or quantum wires. I mean, basically the density of states shape will change, but what will not change typically are stuff sitting in the front and all that. It won't change, and the Fermi function difference is not going to change. And that's your absorption coefficient. So as an example, you are solving in your assignment. You're kind of so I've given you a problem here where you are going to explain it's called a gain spectrum, and all of them is related to this absorption spectrum. So you're going to explain why does this gain spectrum for a quantum well look like that, and the reason it looks like that, qualitatively at least. This is gain spectrum of a laser, but essentially what you have is this is your absorption coefficient. This is a figure of the absorption coefficient, except absorption coefficient is negative, which means you have optical gain. Instead of losing photons, you are gaining photons now, and so it's flipped around, and it's a quantum well. So a quantum well ideally has a 2D density of states, so it should be step, but then you have one step and you have another step because there are multiple subbands and transitions. So that's how it looks for a 2D system. And after we go through the derivation today, hopefully it'll be clear how to work through that.
Why does it drop to negative at high temperatures?
That's when you actually, so that's at high energies. You actually start absorbing rather than, so remember we are going to talk about it. When the photons go through the solid or the semiconductor, and what comes out on this side is e to the power minus alpha times the distance through which it goes through. Now if absorption coefficient is positive, then you're losing photons as it go through, but if your absorption coefficient is negative, you have gain. And what it's showing is if my photon energy is here, then I am reducing more photons, I have gain. If my photon energy is here, I have loss, I'm losing those photons. So that's yeah. And the way you get gain is by playing with this term, which is you make, you have to create a population inversion. You have to have these states occupied and these states empty here. You have to flip stuff around, and that's how you get gain, and that's how you make the laser. All right, so let's get back and look at the microscopic processes here, and then get to that point today. Okay, so By the way, pretty much everything I'm talking about is written up in the chapter in the handouts, also very well described in this handout number 29. Maybe I can outline briefly what we are going to look at. We are not going to start with Fermi golden rule, but essentially we'll first look at how do I model light, or how do I model a photon that an electron might see, and then go to the semiconductor and say that I know the states of the electron in the semiconductor, and then I use the Fermi golden rule to see how electrons are scattered from one state to another using that potential that the light creates. So that's the general strategy here. And then by using that and summing up, if I have a certain number of photons coming in, I sum up all possibilities of electrons here that can get promoted to the top by absorbing photons, and that's your absorption coefficient quantitatively. So that's how we're going to look at this problem. And in this process, we will find that there will be, energy conservation. There's momentum conservation. Because of momentum conservation, we'll see that processes like this, like just within one band, within conduction band, will not be allowed. Processes like this will, for large enough photon energies, they're going to be extremely low. Nothing I say is not allowed is like not 100% allowed. There is a very small probability. Because if you have, free carrier absorption, as you know, requires a little bit of that. But this will be the strong process, interband. We'll see that, and we'll see why. Why is it that one process is way stronger than the other, and that sort of thing. And whenever that happens, the photon wavelength, the photon momentum is way smaller than the initial and final electron momenta. Therefore, this is almost vertical. So that's going to go vertically. So it won't change its k too much, and then we'll work through the details, and then kind of end up some amount of detail I describe, and then essentially finally we have to kind of sum up all possible absorption processes by summing up all the states in the bands, and that's when you can see that it's starting to look like what I wrote here. And finally we'll end up there with a full-blown formula that looks something like that. Okay, so that will be your absorption coefficient. That will be kind of the joint density of states. So it's going to write in that. Okay, for three-dimensional semiconductors, it's going to look like that. And here's your band edge. And if I have, again, physically, just to repeat, if the photon energy is smaller than the band gap, not much absorption. As I start increasing the photon energy just above the gap, the strength of absorption is proportional to the joint density of states. And joint density of states depends on the dimensionality or nanostructure. If you have 3 dimensions, if you have 2 dimensions, it's going to be a staircase. If it is 1 dimension, it's going to be kind of 1 over square root and all that. So you can change the absorption coefficient spectrum by playing with nanostructures. So you can change it in a very interesting way. So most of the lasers that are used today to power communication to send signals into optical fibers are not bulk; they are quantum well based. So they have like staircase sort of joint density of states, and so let me just skip through a couple of them. And they're made of for 1.55 micron, which is the wavelength used for optical communications. Typically, it's a combination of indium, gallium arsenide, and that sort of thing. You choose the right band gap based on quantum well thicknesses and all that. And there's some details here. Let me go to the point I wanted to make. So if I make my absorption coefficient negative, I get optical gain, and by using that, so the way I do that is my normal equilibrium absorption coefficient is like this. If all the valence band states are occupied and all conduction band states are empty, then I have absorption coefficient. The moment the photon energy is larger than this much, it's going to get absorbed, right? Because it can kick this up here, right? But if I create a situation by injecting a lot of holes into the p-type and injecting into the valence band and emptying out a lot of states here, okay? And I inject a lot of electrons. I fill up this band by injecting electrons. Jn is bringing in a lot of electrons. Jp is bringing a lot of holes. Another way to look at it is I'm pulling out electrons from here very fast. So now I have created, a function that's upside down. Here occupied here. This is unoccupied. And in that case, Fv is say 0, Fc is 1, right? So I started with this being 1, this being 0. Now, if I create this very highly non-equilibrium situation, I flip it and it becomes negative. And that's how this kind of flips sign, right? And then you get your window within which your absorption coefficient that has become negative. That means if I have now photons coming in, 10 photons coming in, I have 15 going out. And what is amazing is this is called stimulated emission. We won't get too much into the physics of it, but the photon that comes out because of this process is an exact clone of the photon that came in. Clone in every sense, in energy, in phase, in direction, everything it's a clone. It's not like it's the same energy but a different momentum. Everything is a clone. So that's called stimulated emission. It is one of the most amazing things that happens in nature, and it's kind of amazing people figured it out in the last, since 50s and 60s is when people figured this whole thing out. And that's the heart of how a laser is made. Yeah,
Are there other applications other than lasers where you would take advantage of the negative optical gain?
Quite a few, yeah. No, that's a good point. So let's say you want to build an optical amplifier. You have photons and somehow it's, you want to regenerate them. So you just, use this. So this is called a SOA, or a semiconductor optical amplifier.
Is that in fiber optics?
Yes, absolutely. In a lot of the optical communication systems, you have, even in fiber optic signals, there's a certain decay length, meaning photon intensity decays, and you've got to boost it back, and this is an amplifier, and so it's going to boost it back up. And quite a few others. I mean, you want to generate ultra short pulses, of femtosecond pulses of laser light. You can have, a circuit in which you have a little feedback and gain and all that. So this is a gain element. It kind of, whenever you need to, you can imagine if you want to produce a clone of a photon state, it can have amazingly large number of applications, and so this is at least qualitatively, hopefully the process is clear, and quantitatively you have to work through this math a little bit here. So yeah. Okay, so there is another very interesting thing that happens here, that if my absorption coefficient became negative, but then at large enough energy it's going to go back up. When you plot this function, difference for occupation function, you'll see that it will, again at a certain energy, it will cross 0 and go back up again. And that means it's very interesting. Now, if let's say I'm sitting here, I've injected electrons and holes, and I've created this sort of non-equilibrium situation. And here you will get optical gain. You will get photon in, in will have photon out. But if you look at here, if the photon energy is h bar omega is here, now this energy is larger than the band gap. But there's no absorption whatsoever. The material is completely transparent. Does that make sense? I mean, if my absorption coefficient is 0, then this material is transparent. If I have 100 photons come in, I have 100 photons go out, as if it was not there, right? So that's called optically induced transparency. So you are, under equilibrium conditions, this material is going to absorb, right? But by injecting a certain amount of current into it, and creating a non-equilibrium situation just right, I can make this material transparent to that photon energy. So it's an active transparency, or optically induced transparency. Another very interesting effect. Yeah.
Is that because you're injecting enough into the conduction band but leaving enough in the valence band that the net gain you'd get is equal to
exactly.
the net loss? Okay.
That's right. I mean, that's exactly right, because you can see that gain and loss are exactly balanced here. So yeah, right. Now, and then it has some pretty interesting other applications as well. The way this is realized in a real semiconductor nanostructure is you have your quantum well. You have designed your states here, chosen your wavelength by designing the quantum well thickness and all that, right? Material choice and the thickness of the quantum well will let you design the exact wavelength of light, right? And let's say you go from the ground state here to the ground, the ground state here, but then to inject electrons that you need to fill the conduction band, we need an N-type contact. So I have a doped semiconductor next to it. Right? And I similarly, to create holes in the valence band, I need to have a acceptor doped p-type semiconductor next to it. And I put them together, my energy band diagram may look something like that. You have a problem in your current assignment where for all kinds of choices of bands and offsets, you're going to draw the energy band diagram. If I dope it n-type here, p-type there, and all that, how does the equilibrium band diagram look? There's only one magic to this. At equilibrium, the band diagram is such that the Fermi level is the same everywhere, right? And everything else has to adjust. Conduction band, valence band, they have to bend accordingly and the band offsets do not change. Band offsets do not change with whether you dope it or don't dope it and all that. So those two things are your boundary conditions, and then you put them together. Here's an example of a laser diode heterostructure, quantum well laser diode structure, which is at equilibrium when you're not injecting any current. When you're not injecting any current, your absorption coefficient looks, it is going to absorb the photons, right? When you try to pass photons through this way. But now when I inject it, I create a lot of electrons and I split my Fermi levels. One of the Fermi level goes into the conduction band, the other goes into the valence band, and the difference between them is equal to the applied voltage. Just like, remember, for the ballistic FET, source and drain, you have two Fermi levels that separate by drain voltage. It's very similar here. It's really no different. What happened here? Okay, so and this is how you have created population inversion. Now your Fermi level is in the conduction band here, and Fermi level for valence band is here now, and then that's how you create this sort of situation, and you get a negative absorption coefficient. Just a second, and then this is a picture. In pictures are energy band diagrams, how this process is created. And remember, if I have photons coming out here, so there'll be transition from conduction to valence band here, but after you inject. Physically, what you're really doing is the electron comes in, drops here and then drops here. This process is going to just emit some phonons, and it's going to heat. This process from here to here is going to create light. And then that electron is going out that way. Electron going out that way is same as hole coming this way. It's kind of the same picture. So the electron, you're kind of cascading it down, and one of those sections is going to emit light. So that's the idea of any LED or laser or anything like that. And physically, this is how it looks. You have the quantum well regions here. You have metal, N contact at the bottom, P contact on top. All the active region quantum wells are buried inside here, and it's typically a long ridge, and the photons kind of bounce back and forth, and you have to build a cavity to make a laser. That's a feedback mechanism, and then it comes out from one of the sides. So the laser light would come out from one of the sides here. In the class, we saw a demo of a blue laser. It's the exactly same structure. They use indium gallium nitride. There's a ridge. And then, these two flat surfaces are the two mirrors, and the photon bounces back and forth and kind of gets out. Two questions. Okay.
So the band offsets in these semiconductors, can those actually change if you're working with correlated materials?
I think that answer is not known today. If I have a correlated electron solid, whether the band offset depends on voltages or not, most likely it will change because you're changing the band structure, you are opening up maybe a Mott-Hubbard gap or something like that. But in semiconductors with single particle physics, it does not change. And actually it kind of starts changing if I have two-dimensional crystals, where you don't have strong chemical bonding, I have van der Waals bonding, then the offsets are not fixed, they're not locked, they can change. But in three-dimensional semiconductor solids which are non-correlated, it doesn't change. So that's good. Yeah.
I had always been under the misconception or conception that you needed a continuous transition between the Fermi levels spatially. Is that false? That is, like, the Fermi level on the left and the right need to continuously switch from one to the other.
Yeah. So that's a very good point. If I have two bands, right? Well, here I have two bands. I have a conduction band and the valence band, right? So when my system is in equilibrium, then there's only one Fermi level, and that Fermi level may change in space. If it's in equilibrium, then the Fermi level is not going to change in space either. Now, but then in a PN diode, what I'm doing now is I have formed two ohmic contacts, one to the N band or the conduction band, the other to the valence band. I have formed two ohmic contacts, and now they are, a metal connected to this, a metal connected to that, and they are now connected through a battery. Okay? So now I have two Fermi levels. I can define two Fermi levels that one of them is saying that the conduction band is in equilibrium with this contact, valence band is. So now I have a splitting of the Fermi level, except you're right that, so if I were to follow the Fermi level of electrons, then it will go like that, and it will kind of go over here and join here. So Fermi level of holes, it will go over there and kind of join here. And in fact, there is light emission occurring also in these regions. That's just something we do in a device physics course. Whenever I have EF of electrons and EF of holes separated, it's a non-equilibrium situation. It will try to remove electrons and holes either by non-radiative recombination or by radiative recombination.
Would these be quasi-Fermi levels then?
Yes, these are quasi-Fermi levels. Whenever I have any voltage applied, it's a non-equilibrium situation. It's always a quasi-Fermi level. So, okay, yeah. Okay, so that's how it looks, and physically, you can package it. The diode would look something like really small here, and a wire bond that injects the current that creates this non-equilibrium situation, and then it's commercially packaged inside, more something like that. You have electrical current maybe coming in from here, and an optical fiber that comes out takes the photons out. Okay, so that's a very quick summary. Let's now delve into a little bit of the details of this problem. Okay. Now, so we'll start with just kind of a very quick recap of light itself, because this is a light and matter interaction of light with semiconductors. So let's look at light. How do we explain or understand light? And remember, our strategy is that we are going to look at how many, what's the rate at which electrons absorb these photons. And what's the rate, and then what's the absorption coefficient. So let's define the absorption coefficient accurately first, and that will motivate how to write about light and what should be. So absorption coefficient now is this is a three-dimensional solid, a semiconductor chunk. Inside it, I could have quantum wells, whatever be it, quantum dots and all that. But in general, this is a three-dimensional solid, and I have light incident from the left side, and I have light coming out from the right side. And what is the absorption coefficient? I can write it in this way. It's the number of photons absorbed, right, per unit volume per second, or inside the solid. That's the numerator. Remember, the absorption coefficient has units of what? Inverse centimeters, right? Right, because this is a length and intensity is decaying, so it's in inverse centimeters. So number of photons absorbed per unit volume inside this solid per second divided by what should I have in the denominator? Number of photons that are incident, right, on it per unit area. This we are going to use it as it's going to be a plane wave moving in this way with an oscillating electric magnetic field. So number of photons incident per area per unit second, right? So that's the physical way of writing absorption coefficient, and that is the way we are going to use. So we have to calculate two things. We have to calculate the denominator and the numerator, and we'll show that it will end up being this formula. So that's the absorption coefficient quantitatively. So let's start with the denominator, number of photons incident per unit area per unit time. Maybe I can ask you first, how do I do that? This is not a semiconductor problem. This is an electromagnetic theory problem. How do I find, if I have light coming in from here, how do I find how many photons are coming per unit area per unit time? So for that, let's actually go back to, we kind of do very quick recap of Maxwell's equations and what is light, and I don't want to spend too much time. That's EC 3030. There are many other courses where you go through that in quite some detail. But essentially, light, I think we know for 2 centuries now, is a oscillation of electric and magnetic fields, an oscillating electromagnetic wave. But even before that, whenever I have an electric field is related to charge, right? I mean, let me write down the Maxwell's equations. If I have electric field, and the electric field is created because of electric charge, right? And then a positive charge is going to basically, in some sense, radiate electric field away from it. The electric field lines will start out from a positive charge. And let's say instead of one charge, I have a certain charge density rho in coulombs per meter cube or centimeter cube. This is the charge density of charge. I can have this may be the proton of an atom, in which case I have maybe 10 protons in it, or it could be a charged 2 meter large ball of metal. Doesn't matter. This is the same thing. Electric field will look like that, right, around it, and that is captured by the first Maxwell equation, which is called Gauss law, that electric field lines are going to diverge away from a positive charge, right? It's going to, so the divergence of electric field is equal to the charge density. Right? So that's the physical meaning, right? Divergence of electric field is equal to, actually I should write it, let's write it that way. The electric field times the permittivity of vacuum is equal to displacement vector. Okay? And typically we should write it as this over epsilon naught. That's the right way of writing it. So displacement vector is a flux density of electric field. Okay? So that's Gauss law. If I have no charge, right? If I have no charge, it's saying that that doesn't imply that I have no electric field. It just says that divergence is 0, right? That's all it says. The divergence is 0 if I have no charge, and that in the vast stretches of space, we have no charge in deep space, but the light can go through it, right? That's the electromagnetic wave. Yeah.
Epsilon naught is permittivity of free space.
That's right. Permittivity of free space, right?
So we don't take relative permittivity of the material.
That's a good point. So we can, and in general, you have electric field plus a polarization. And the polarization has like an electric susceptibility times electric field. So if I were to write all of this together, I should have epsilon naught 1 plus susceptibility times electric field, and that's what we call as a relative dielectric constant. If I have atoms in the way that can screen the electric field, that's your relative dielectric constant. So in general, if I have a material, then I should have the relative dielectric constant here as well. I'm just kind of writing light as in vacuum now for now. So that's the first Maxwell equation or Gauss law. Similarly, you have a Gauss law for magnetic field, and at least till today, nobody has found a point source of magnetic field. Fundamental physics doesn't forbid it, but at least experimentally, except 1 or 2 papers, people have said it's really 0. So let's keep it like that for now. Right? Divergence of magnetic field is 0. What is it? So again, just to be clear, if I have positive charge, field lines will go out from there, and if I have negative charge, the divergence is inwards, right? The field lines come in. So it's a sink source or a sink, right? So that's what this law is saying. It is a very physical law. And if its charge is 0, you can write electric field as minus gradient of a potential, and that's your Laplacian equation. Del squared phi is equal to. So you can solve your potential problems for all kinds of metal objects or all that, or semiconductors, whatever be it. All right. So that's about electric and magnetic field spatial dependence. Now, the amazing part about electromagnetic waves is, of course, what happens when you start, playing with time. So, if I look at, does electric field actually have a curl? Does it have like whirlpool-like nature? I mean, does it curl around something, right? So, curl of electric field is only possible, and this was discovered by Michael Faraday, right? Called Faraday's law, that if I have a time-varying magnetic field, if I have a magnetic field that's increasing, decreasing, oscillating, but if it is changing with time, it's going to give electric field a curl, and then it will be able to electric field. Okay, so that's Faraday's law, and finally you have what used to be called Ampere's law, that a time-varying magnetic field leads to an electric field, and a time-varying okay, so if I look at the curl of a magnetic field, where, let me write that down. This is D vector, and similarly I can write for magnetic fields, B is mu. If I have vacuum, mu naught times H. This is called a magnetic induction or something like that. This is Tesla. This is in amps per meter units. So curl of this magnetic induction, which is related to the magnetic field this way, is equal to a conduction current due to physical particles like electrons or atoms or ions or plasma, whatever be it, physical particles, plus rate of change of a displacement vector, which is, the epsilon times E. So that's related to that. Before Maxwell came, there was no such term, right? And this was called Ampere's law, right? Ampere's law said that if I have a current flowing, J in a wire, then if J is like that, around it, there'll be a curling magnetic field, right? There'll be a magnetic field that will be curling around it, right? Like that. And then this is kind of Biot-Savart law and all that sort of thing. A current carrying wire, DC current carrying wire creates a DC magnetic field around it. But Maxwell came and said that if you just write that Ampere's law, then you will be in a bit of a problem. It will violate what's called continuity equation. So, meaning if I have charge that's changing in time, I must have this term. If not, I'm going to violate continuity equation. And he introduced this term. It's called the displacement current. Or in other words, I can create a magnetic field if I have a time varying, D and E are interchangeable, time varying electric field. That's what the physical meaning. So you can see there's a nice symmetry to it. A time varying magnetic field can create an electric field. Time varying electric field can create a magnetic field. Right? So the amazing part now is if I take, just a very simple experiment. I take a metal wire and I connect to it an AC battery, and I apply. I try to inject, apply voltage. So essentially, an AC battery like that will have a amplitude e to the power or sine omega t, let's say, right? And it's going to just try to move electrons back and forth. There's no net current. It's an open wire, but it's going to just move electrons back and forth. And when I move electrons back and forth, you can see both my current is changing in time, if you might. So that can, if what I'll create is kind of electron charge. Some, it'll bunch up here, it'll be less here, and all that. So this can create a time-varying electric field or time-varying magnetic field, because the current around it is also going to change. The magnetic field is going to change. So it will create a time-varying magnetic field that may look like that. That will create a time-varying electric field and a time-varying magnetic field. And essentially, that's, what's amazing is you can, so this part of the time-varying oscillations can become detached. They can detach from the source, and they don't have to be connected to the source. They can detach, and then they can sustain each other forever. Basically, they don't need the source anymore, right? So a little bit of time variation of magnetic field. So basically, when the magnetic field dies, it creates large electric field. When the electric field dies, it creates large magnetic field. So they kind of create each other, and this is what's called light. This will basically propagate forever till it gets absorbed by a semiconductor or something else, right? So this is the classical picture of creation of light, and quantitatively Maxwell showed very beautifully from here that you can get that in a couple of steps, right? And you can get the speed of light from here as well. So let's look at these two equations, right? I think I don't know whether I should try to derive it. Basically, you see that here curl of electric field is minus dB over dt, right? And B is mu naught H, which is this is the permeability or magnetic permeability of vacuum times H. But then the curl of H is related to electric field through here. So you kind of take a curl again, and that's how Maxwell gets curl and d by dt are interchangeable because that's a time derivative, that's a spatial derivative. They don't interfere with each other's job. You can move them back and forth. And then essentially curl of curl, well, okay, so it looks gradient of divergence. That's the way it looks. Minus del squared. This is a identity. Mu naught and curl of H. Let's look at free space. In free space, there are no atoms. There can't be any conduction current in free space in vacuum. Okay? So in that case, that term goes to 0, and you get a d over d, the d over dt, and that thing is epsilon naught times electric field. Sorry, I think you get a time squared because there's already a d by dt sitting here. Yeah. Okay, so what you get here is, again, in free space, what is this? That is also 0 because I don't have any free charge either in free space. So that's 0 as well, and you get, I think, for what many people consider is one of the most beautiful equations ever, right? So you get mu naught epsilon naught d2 by dt squared of electric field is equal to 0. And so that's your wave equation. So mu naught times epsilon naught is exactly equal to 1 over speed of light whole square. Right? 1 over speed of light whole square, 3 times 10 to the power 8 meters per second. That's the speed of light. And so what it's saying is, this is a solution for all Maxwell's equations, or this is a solution for this 4 set of equations. If I can find an electric field that satisfies the spatial derivative like that and time derivative like that, and they are connected, right? Spatial derivative and time derivative connected through the speed of light. The ratio of rate of change in space divided by rate of change in time is speed of light. That's the meaning of this. That's how fast the electric field is changing. And so from here, you can see that the electric field will be some unit vector. It's a vector field times an amplitude of the electric field times e to the power I. Let's write it this way: k dot r minus omega t. So it's a wave equation. What we're saying is, let's try to solve it. Let's find a solution to it. Okay? And here's our trial solution. If electric field is a wave, hopefully you can see the exact analogy between the phonons that we did in the last class. We said, okay, here's the equation. Here's the differential equation for phonon vibrations. Now here's the differential equation for electric field vibrations in space. Now this is the same thing for magnetic field too. Basically, if you replace it with H, it's the same equation. Right? So everything kind of changes in this way. Okay, so if you substitute it here, this is a very specific wave which has a unique omega and a unique k. And what are we doing here? We are trying to find the dispersion omega versus k for light now. So this is an expression for monochromatic light or laser light, one wavelength or one frequency. So your real light is composed of a sum over many wavelengths with some amplitude and all that. Many wavelengths, but this is a monochromatic light, or it's a single mode of the photon field or the light field. If I substitute it here, you can see that this is del squared. Let's look at this. If I take del of e to the power I k dot r minus omega t, right? What will I get? It's a derivative. It's going to pull ik out, right? So you get a ik times e to the power I. That's what it's going to give me, right? Remember, so it's a scalar, but the del it's a gradient, so it took it and converted it into a vector here. Now if you do it twice, then you get ik squared, right? Del squared. Del squared of the same thing is going to give you ik squared e to the power I, k dot r minus omega t. So in kind of for a monochromatic wave, your operator del is equivalent to multiplying the thing by ik. That's what we're doing. It's the same thing. And in fact, I don't want to prove this, but if you take del dot, that means you can show that it will be ik dot of whatever sits to the right. Same thing. I mean, maybe it's obvious, maybe it's not, but I'm just saying that, okay, so you can prove it. Del cross a vector function here will also be equivalent to ik cross product with that function here. Right? So del is replaceable, or the gradient is this operator is replaceable by ik for a monochromatic wave. Similarly, the other thing we need is d by dt's. Okay? Now d by dt's is very easy, right? Del over del t of this quantity k dot r minus omega t, right? What is that? So again, it's going to pull out minus I omega to the front, right? And so minus I omega comes to the front, and you retains this part. So del over del t is interchangeable with multiplying by minus I omega, right? So that's what we really want to say here, and this is all true for a monochromatic wave or a light wave with one frequency. And if you find 5 frequencies, this is true for them individually. It's true for them individually, separately. So if you have a linear superposition, just make sure your coefficients are the same, and you can use this for each one of them individually. But the k's that will come out here and the omegas that will come out here will be different. So that's the thing. Yeah. Okay. So now if that's the case, we can kind of use this for a monochromatic wave and see. If I substitute it here, del squared is going to give me what? Yeah. Right. So essentially, it's going to give me my ik absolute squared, right? Del is like that, and 1 over c squared d by dt is going to give me minus I omega squared, right? All right, let's write it ik squared. Why do I do that times E naught equal to 0, right? And there'll be some hat and all that, but that's fine. So that's your equation. And then from here you can, I think I did. What did I do here? Del. Right. So minus I omega. That's right. So and you can see from here I get omega is c times k, because my electric field amplitude is not 0. If it's 0, there's nothing to talk about. There's no light, right? But you can see that now this is the necessary condition for any sort of electric field to satisfy, to be eligible to model light. So this is if this is the electric field, its frequency is related to its k, which is 2 pi by its wavelength, by this relation, and that ratio is just the speed of light, right? Omega is c times k. Yesterday we saw the same deal, but for phonons, right? We saw omega was sound velocity times k, right? Here it's light frequency. Phonon frequency is equal to sound. Acoustic phonons was related to sound velocity. Here it's related to speed of light. There are a couple of other things you can get out of it very nicely. If I look at del dot E, what was it doing there? Okay, so let's look at this relation. Del cross E is equal to minus dB by dt. So from here, what you get is I k cross, del is ik, cross E must be equal to minus of d by dt is minus I omega, so we get a minus I omega times B, right? Right? So cancel your i's from the both side, and what you get now is very interesting result, that k cross E, if I have a monochromatic wave which has a k, which is a wave vector, defines its direction and its wavelength, k cross E is equal to omega times B, and omega we know is c times k, right? And that. Now, it gives us two very important things. One is the direction of that wave, right? Here it's saying that the direction of the magnetic field is perpendicular to both k and the electric field, right? So this is what you call as a plane wave of light. So if that's electric field and the wave is going to the right, and if the k is 2 pi by wavelength times the direction, then the magnetic field must be perpendicular to both of them, right? And that's what it's saying here. K K cross E is equal to that. And so B must be like that, and E cross B is going to be the direction in which the wave is going. You know, this is the right-hand rule, E cross B. Now, the other very interesting thing here, and this is an electromagnetic wave where the electric field is oscillating in time, and the magnetic field is also going to oscillate. So this is, you know, like that. Electric field will flip sign, that's flip sign, but they always flip sign in tandem. You know, so that's the electromagnetic wave. The other very important thing is you can take magnitudes of both sides. Okay, electric field times K on the left side is equal to C times K times magnetic field on the right side. See what I'm doing? I mean, this is magnitudes, just, you know, absolute values, right? In which case you see that the K's will go away, and the electric field strength at any point in here is equal to speed of light times the magnetic field strength, or the amplitude of electric field for a light wave is equal to, and light, so electric field divided by magnetic field amplitude is equal to the speed of light. So though they have different units, you can one can kind of qualitatively say that the electric force is way stronger than the magnetic force, because remember, electric force is Q times electric field, right? But magnetic force is velocity times this, right, of a particle, and then you can kind of see the ratio will be like V over C squared and all that. But the strength with which an electric field part of the electromagnetic wave can move charge is way stronger than the strength with which the magnetic field part of it can move charges, electric charges. It's an important point. And so most of the interaction is primarily through the electric field. I mean, there's always a part which is due to the magnetic field too, but most of it is due to the electric field. It's way stronger. Okay. And finally, we can define another vector here called the magnetic vector potential. So, and this is what enters the quantum mechanics of electrons. Directly, the magnetic field directly doesn't enter electromagnetic wave. Electromagnetic waves enter the interaction with electrons through what we're going to refer to as the magnetic vector potential. And the magnetic vector potential is very simply, you know, okay, so what's the need for a magnetic vector potential? We know that if I have, you know, electric charge, if I have electric field, I can write it as negative the gradient of a scalar potential, which is what we call as the voltage, or the potential, right? And this is possible because you know, I can have okay, so basically curl of you know, because I have curl of E is equal to this, I have something non-zero. You know, I can turn off this part and I can get a curl of electric field that's 0. This is what's called a gauge field. I don't want to kind of get into that part right now. Essentially, you can define a scalar field whose gradient will be the electric field. It's called conservative forces and all that. But you can't do that for a magnetic field. It's not possible. It's not equal to of a magnetic field. It's not possible because a magnetic field is, you know, if I have a conduction current, magnetic field curl is not 0. You know, so I can't do that. Even if I have a constant DC conduction current, it's not 0. So I can't do that. But I can do it as a curl of a vector field, and that vector field is called the vector potential. You know, magnetic field is curl of a vector potential. That's what we're gonna try to get to right now. Now, physically, what does that vector potential mean? The force on a charge due to magnetic field is Q times V cross B, right? This is the Lorentz force on a charge classically. Now, we can, you know, look at its, you know, just in terms of its magnitude. It's kind of like that, V cross B, but, you know, forget about the direction for a second. The strength of it is like that, right? And so that's the force. And force, we know in quantum mechanics is what? dk dt, right? The electron sees, if it sees a force, its k changes. If it's in electrons are in a semiconductor, it has certain k's. The k starts changing because of that force, be it electric force, be it magnetic force. Now, B we just said is del cross A. Del cross A, you know, in scalar quantities, just d by dx or d by dy and all that, right? this is the is the curl, but so it's d by it's a derivative of that. Right? So I'm just looking at what is the physical meaning of it. Right? What is the physical meaning of the vector potential? And you can see right away, dt's all go away, and what you realize is electron charge times a vector potential is equal to change in the momentum. Right? You see that? I mean, the vector potential causes a change in the electron momentum, right? Directly from here. Is that clear? I mean, this is a we're looking at the units, and from there trying to kind of coax out some physics from there, right? But that's physically true. The vector potential is going to be directly related to the change in the momentum of an electron. And the way it enters quantum mechanics is the way light enters quantum mechanics is in this way. So I'll just kind of write that down, and then I'll outline the process of the interband absorption. You can see it's a kind of a long process, but we wanted to see how exactly should we look at light so that we are able to model how it may or understand how it may interact with matter in form of electrons. So from here, if I look at an electron in a solid or a free electron, so its total energy of the electron would be given. Just one more thing. Let me finish this part up. I erased that. So the number of photons then that are incident and are incident on the surface here. The number of photons is given by the energy, right? Right, energy divided by the total energy divided by speed and all that. So we kind of have to think about that. And I think what's called the Poynting vector in electromagnetic theory. So if I find E and H, E cross H is the rate of flow of energy. E cross H is rate of flow of energy because of the electromagnetic wave. So I take electric field, which is E naught, that sort of thing. When I know electric field and magnetic field are related through speed of light, right? And when I kind of combine all of that, what I'll get is a very simple relation: amplitude of electric field square by twice what we call as the impedance of the free space, right? Impedance of free space times whatever direction you are going in, k hat. So it's a Poynting vector that's carrying this much energy per unit time, per unit area. But that's the total energy, and we want the number of photons. I don't want just the energy, I want the number of photons. Now each photon, because I've considered a monochromatic wave, has an exact energy of h bar omega, right? Because if the frequency is omega, the energy is h bar omega for the photon. So therefore the denominator in that thing is s over h bar omega. This is actually a time averaged s, so kind of think about that. This whole thing divided by h bar omega is the denominator of your absorption coefficient, which is how many photons are incident per unit area per unit time. So you can do that. If you look at sunlight, you will find typical sunlight electric field amplitude would be about 1,000 volts per meter. That's how much is the strength, and you can calculate. Obviously, deep in the night the number would be 0, but normal daytime it would be a few billions. For example, when you do this number for say visible light of a certain wavelength, you will see it's a few billions or something. It's a large number of photons. Okay, so that's your denominator, and the numerator now for absorption coefficient is how much of it is absorbed. We need to talk about the interaction of this light with the electrons. Right? Okay, so this is all written up in the short chapter on Maxwell's equations, whatever we discussed here. So now we are going to talk about how it absorbs, how the electrons will see the photons, and I think you can kind of see that the electron without the photon has energy that is, again, it's kinetic plus potential, very standard, right? It's electron, no matter where it is, it's electron in a hydrogen atom or in a semiconductor, it has a certain kinetic energy related by this term is the potential energy. This is what we call as the Hamiltonian or the total energy, right? But we just said that if I have light, then light changes the momentum of the electron. And I don't want to justify it. This can be rigorously proven. But this momentum operator which used to be in quantum mechanics minus I h bar times the gradient, right? It changes to this quantity. You have a momentum because of the kind of the normal, this term, plus you get another kick, which is q times the vector potential. Q times vector potential is, you can see this is kind of the momentum. So it gets a little kick because of that. And instead of Q, I'm going to just write E here because that's consistent with the notes. E is electron charge. So instead of momentum being just minus I h bar gradient, in the presence of an electromagnetic wave, that's how the light enters into the energy of matter. It changes the momentum operator to that. So this part. Okay, so I don't want to get into more details, but that's, yeah.
P hat still the regular momentum.
Correct. P hat is still the regular momentum. And so that's, P hat is minus I h bar times the gradient. So that's how it enters there. I'm not trying to prove it, but I've given you some sort of a, feel for why it should be the case. And you can rigorously prove it from, Lagrangians and all that sort of thing. You can find it in textbooks and all that. So now, what we're going to say is now, specifically, so if you want to treat a hydrogen atom or a nitrogen molecule or some big chain polymer, you can calculate how light might interact with it. We are interested specifically in a semiconductor. In a semiconductor specifically, this is periodic, right? The electron sees a periodic potential, right? And we have solved that part of the problem. So what I'm going to do is try to bring it to a situation, because we have done all the hard work doing effective mass theory, looking at how to handle quantum structures and all that. Let's bring it into, bring all those things in to simplify this problem. So the first step we do is you open out this square and you say p square by 2 m naught plus v of r. I'm just going to kind of rewrite this thing. P square by 2 m naught plus, now these two are, this is an operator, so when I open a square, I must be a little careful not changing orders and all that. I just want to be a little careful. So I keep it as E over 2 m naught times, so I take P dot A. A is the vector potential. Plus, so when you do A plus B whole square, you get a 2AB, but here I'm writing it as AB plus BA. I don't want to mess up their order, because these are operators, right? So I write plus A dot P. Right? So that's your, I opened up, we're done with A square, we're done with AB, 2AB, but I need to also have B squared, and that's E squared times. So that's your full, that's your Hamiltonian of the electron system that's interacting with light. I don't want to say it's the full Hamiltonian, because this is not, if you want to go the full all the way to the quantized light field as well, you must have another term here, which is like a harmonic oscillator of light and plus half. That would lead to quantum electrodynamics and all that, but we're not interested in that at this point. We're looking at large number of photons. Photon field is a classical field, comes in, and this many photons are incident on it, on the electrons, and we're looking at the electron problem, how many photons it can absorb. All the photon details are buried inside the vector potential. That takes care of all that. Okay, so now to solve this part, here's the way we are going to approach this problem. First of all, just like in a scalar field, you have an option to choose whatever potential you want as your ground. You can choose whatever it is. The physics is not going to change. Similarly, in vector fields also, you have a choice of what's called a gauge. Just like a scalar, I choose V naught is equal to 1 volt as my ground, and then I look at everything with respect to it. Similarly, for vector potentials, here's what's called this is an example of a gauge. It's a vector identity. Divergence of vector potential is 0. I'm going to choose only those set of values for which. So this is called a Coulomb gauge. Then there are other gauges like a Landau gauge and all that sort of thing. These are just effectively the same thing as this. It's choosing a certain value, and it doesn't change the physics of the problem. The gauge choice is called physical laws are gauge invariant. And that's what we're doing here. And we're choosing del of A to be 0. If that is so, one can show, and I'm not doing it now, these two terms are exactly the same. You can flip them, they are the same. If del of A, or divergence of A is 0, then they're exactly the same, in which case, I'm going to just retain the A dot P. And that's, many books would, or rather many places I would kind of start from here, say that this is your term, this is your electron phonon Hamiltonian. I just want to show where it comes from. It comes from vector potential. Vector potential changes momentum, that changes that, and you end up here. So now we are going to look at photon fields where the photon intensity is not terribly high. Okay, so the way I want to justify it is I'll say that term is what's called a nonlinear term in light, nonlinear optical term. We're going to say that term, you can compare it with this term. You can see that if momentum of the electron is much larger than E times A, from here, momentum of the electron is much larger than E times A, this term will be much smaller than that term, so I can throw it out. And as an order of magnitude, the momentum of the electron, maybe you can tell me classically, what is the order of the momentum of an electron in a semiconductor? Remember, these are semiconductors, these band edges occur because of Bragg reflections at pi over a k's. The k, it looks like 0 here, but actually there is a k involved with the g vectors here, right? So the actual momentum of electrons at the band edges is of the order of Planck's constant by the lattice constant, or you can write it as h bar over h bar times g, which is h bar times 2 pi over a, which is h over a. A is the lattice constant, angstroms. Whereas light field, the wavelengths and all will be much, much longer. So we can neglect it. I'm just kind of trying to justify it qualitatively at this point, but quantitatively, if your photon field is large enough, you can neglect it. If you have only one photon, you cannot neglect it. If I have, if you have nonlinear effects, you cannot neglect it. I don't forget about the one photon comment. If I have nonlinear, very high intensity, then I must consider that as well. But I'm not going to look at that effect. I'm just going to kind of neglect that. So I've basically tried to reduce the problem down to a solvable one. And now here, this is the electron Hamiltonian before there was light, before it saw light. That is completely solved. What is the solution to this Hamiltonian? It's a band structure, EK diagram, right? The wave functions for these are, the valence band wave functions look like, some envelope functions. Let's, for 3 dimensions, it looks like e to the power I k v dot r over square root of the volume times the valence band block periodic path. We have, what I'm saying is this part is completely solved, and the energy eigenvalues of these for the conduction band are known because we know the effective mass. Valence band are also known. So we have completely solved this part of the problem, and now we are going to treat this is the perturbation term. Right? This is our perturbation term, or this is our W, which will tell us how states are going to change, how is this state going to get scattered into that state, and all that sort of thing. Does that make sense? Okay, please. So that's the idea again. We have done this also we first did it for impurities, looked at what's the impurity potential and said, okay, how does it scatter, right? Then we yesterday looked at phonons, so phonon potential, and said, how does it scatter electrons from one K to another K? So now we're doing it with light, same thing. There's the light field perturbation term, and how does it change K occupation functions? That's the game now. So your transition, therefore, so this part is exactly solved. You know the energy bands and all that. Transition will be from the valence band to the conduction band. I k conduction band dot r. I'll just sketch this out. U c of r. Okay, so those are the two states: a state in the valence band and a state in the conduction band. With those are the wave functions in the effective mass theory. Okay? Right, this is the envelope function, and this is the periodic part. It's the envelope function, and that's the periodic part. Okay, so now let's see. We have
I missed the reason why you would neglect that last term.
So we are saying that for intensities of, so the last term had mod a squared, right? And that is proportional to the intensity of light. And if the intensity of light is not very large, this is when you get into nonlinear effects and all that, that's when I can neglect that term in comparison to the momentum term, which is p squared by m, and p squared by m is kind of large. So we can find out at what intensities should this be true or false by comparing it with the momentum term. And what I'm trying to say is for most cases, if my semiconductor laser is, say, putting out about 50 milliwatts, it's still valid. 50 milliwatt is just not that term is way smaller than this one. But then if you blast it with a much higher energy intensity, then it can become comparable. So we're not looking at that nonlinear terms. Okay, so let's see. We're kind of running out of time, but I would like to finish this if you have like 10 minutes. Today is the last class. Maybe if you have about 5-10 minutes, I just want to finish this up and so that we have this topic done. Okay, so is that clear? So we are saying that I have my exactly solved problem here, and this is my unsolved problem. I want to find what is the rate of transition. And my numerator for the absorption coefficient, it's actually here. Okay, there you go. So we have already per area times time. So this part, we already derived, it's here, right? The denominator. Now we are asking how many photons are absorbed per unit volume, per unit time. And that we can find by applying Fermi-Golden rule with this perturbation term. Okay. So the Fermi-Golden rule, let's apply it. First, let's look at a picture of what physically is going on here. So physically, I have a conduction band and a valence band. I have photons that are incident, right? And there's an electron sitting in the valence band at, let's say, an energy of EA. Let's call it E sub A. And the state of it, let's say, is labeled as A. Its wave function would be this wave function, valence band wave function. Similarly, so now a photonic transition will kind of lead it to here. That state must be empty. Let's call it B at an energy of EB, and that's state B. It's just label of that state. Okay, so the minimum here. So again, we're going to label this as 0 and write all the valence band states as minus h square k valence. I'm going to use that over 2 times the valence band effective mass. Right? Is that clear? I'm just kind of rewriting the band structure in this way. And similarly, the conduction band states will be given by EC of k is equal to the band gap plus h square k c, the conduction band wave vector, over twice the effective mass of the conduction band. Right? Does that make sense? I mean, just kind of wrote down the full band structure and all that, and now it kind of most of the job is kind of keeping track of every term and kind of looking at it. So this state is going to transition to that state if the photon energy that's coming in matches the energy and it has the right momentum. So energy and momentum are always conserved together, right? So let's write that down. First, I'll kind of write down what I'm after. So if I want to go from A to B, right? If I want to go from A to B, what is the rate of absorption? Because remember, what we are looking at is the number of photons absorbed per second. So that's the rate of absorption, right? And per unit volume. So the rate of absorption, I will find by, so what is this direct rate? It is just, again, the golden rule, the Fermi-Golden rule is 2. And I have starting out from state A and interacts with the light field. This is the term that will sit in the middle, W, and then ends up in B, and then we take the whole thing squared. That's your matrix element squared times a Dirac delta function that conserves the energy. What does that mean? That energy of state B must be equal to energy of state A plus the photon energy, right? So that's EB must be equal to EA plus h bar omega, right? Right. So that's your golden rule for that transition, and that gives you just the rate for that single state, just one state here to there. Right. But then, if I really want to find the rate of this, you can see that it's not quite complete, because this also requires, if this physical process actually has to occur, let's say absorption, rate of absorption, then this state must be occupied, right? Because if it's not occupied, there is nothing to, there is no electron here, so it cannot do that. And that must be empty. Right? And this, remember the Boltzmann equation, it's same deal of scattering, it's the same problem really. So therefore, to find the absorption rate, f of A, f is the occupation function. Okay? F of A, 1 minus f of B. This is a Fermi function. F is the occupation function, so it says what is the probability it's occupied, right? 1 minus is what is the probability it's empty. So you get multiplied by that. Right? So that's your absorption rate for just one state. Now taking into account also the fact that these are electrons, so they must satisfy exclusion principle, Pauli exclusion principle, and therefore they're forced to do Fermi-Dirac distribution, right? So that's just for one k state. And finally, to find out the net absorption coefficient, what should I do? I should sum up all states, right? And when I sum up, I have to sum over not just one band, but both the conduction band and the valence band, because I might have a transition here, maybe some other transitions there, I don't know. I mean, so you have to sum over all states. So therefore, the net absorption rate will be, let's erase that part. I have to do a sum over all states in the conduction band. You can write it as all states in A, all states in B, all A's in valence band, and all B's in conduction band. So that's your total absorption rate. But unfortunately, we have not finished the job yet. When I'm summing over it, we can also add in my spins and valleys and all that. I mean, very standard stuff if I have spins and valleys. Now, spin part, I'm not going to get into any detail here, but there's a little trick to that, in terms of angular momentum and all, but let's not worry about it at this point. These are all upward transitions, okay? Just upward transitions. But the thing is, the semiconductor, if I have an electron here, and this state is empty, this thing is actually free to also emit, right? So you must take that into account as well, right? So that's the net absorption rate, but the emission rate is similarly GSGV, the sum A 2 pi over h bar, and now you must start at B and end up at A, right? B W A. But what's interesting is these two are exactly the same. They don't change. If you remember, it's very similar to the one rule. And then here you must have that E A minus EB minus h bar omega. EA must be EB minus h bar omega times, now B must be occupied and A must be unoccupied. Okay. So you get the whole thing. So the total net upward transition then, the net upward transition, net absorption rate is the difference of the two. Right? The net upward transition, if you might, is given by the difference of the two. So you get GS, GV. One more thing I forgot to say, we are not just really interested in photons absorbed per second, but also per unit volume. So we must also divide by the volume. So in that case, I must have by volume. So the whole expression then, the big expression looks like this, sum h bar. And what I'm saying is these two are the same, so I'm not going to try to write them as separate quantities. The matrix elements are the same. What is amazing is the Dirac delta argument, one is the negative of the other. So they, Dirac delta function, whether you have negative or positive argument, they're also the same. So this also is common between the two. And what you end up getting is EA plus h bar omega. All that happens is you get a difference of these two functions. And then the products again go away. And all you're left with is A minus f of B. Okay, so f of A happens to be the valence band, and B is the conduction band. And so now you can see it's looking, maybe not yet, but it's starting to look. This is where this FV minus FC comes from. Okay, so now I think we are kind of a bit over time. So let me just finish up by saying that there's a little bit of work in finding the matrix element. I've written it out in detail, every step of it. What we have to do is you have to take these two functions and put it, one here and one here, and integrate over space. Your momentum, this quantity has a momentum operator in it, so that will act on the wave functions and all that. So that part needs a little bit of work, but I think I've outlined it, and just in the interest of time, I'll just leave it on, or rather not try to derive it all over again. But once you do that, you are going to end up with this sort of a formula. And okay, so yeah, hopefully you can see now, or rather you can make some sense. When we are summing over all states, you're summing over, integrating over all k states. So that's and you're integrating FV minus FC comes from here, and Dirac delta function is here, right? And when I take the difference, this difference, EB minus EA, you can see now here it's valence band k state minus conduction band k state, minus h bar omega, and this difference is basically just a gap plus h square by twice m star reduced times k squared minus h bar omega. So an h bar omega and EG, they will combine and give you, this term here in the band gap and all that. Okay. So so with all that, what I wanted to kind of end with here is I'm kind of leaving this to you, because I think I'm pretty sure please read through this and work through, because in the assignment I've asked you in 2 of the problems to evaluate it. So read through it. If you have questions, come by. I have a couple of office hours this week, and come by and ask me some of the details. But this should explain, let's see. So the energy conservation is clearly captured by the Dirac delta. The momentum conservation is captured by your matrix element here, and it assumes a photon has very little momentum, so you have a vertical transition. So typical units of these are 10 to the power 5 inverse centimeter, and then that's what was kind of being shown here, as we had probably discussed in the last class. And so these are typical units of the absorption coefficient for various materials of the order of 10 to the power 5. And that means you need about 100 nanometer to end up absorbing everything, all the photons, typically. So yeah, okay. And when you take the ratio, it will be independent of the light field intensity. So it's a property of the semiconductor itself. It's not a property of the light. It's not a property of how intense is the light beam. How much photons a semiconductor can absorb is property of the semiconductor itself, and that's a linear process. So it will become completely independent of the light intensity. It will only depend on the frequency of light, photon energy. So, okay, yeah. Okay, so with that, I think we'll kind of stop here. We could have gotten into some more details, but hopefully we have the outline of how to handle the assignment problems and how one might go about looking at the optical process and absorption coefficients and all that. Okay. Yeah. And if you do have any questions on the, I think the last problem or second last problem is where I've asked you to play with this function and show how can you get negative absorption coefficient. If you have any problem, come by. We can discuss in my office hours or something like that. Okay. Okay. Good. So let's finish up then. It's already way over time. Thank you.